We're moving in section 4.5, which is actually the final section in chapter 4, but we are going to spend a couple days on it because it is looking at more of a complex way to look at integration, and I want to take my time going through it. So before we actually get to this new technique in this new lesson, I want to go back and remind you how the chain rule worked for derivatives. So for example, just kind of throw a problem up here. So our chain rule was our derivative rule that allowed us to work with composite functions. In other words, a function inside a function. We had this inner function, which often was called the letter u. U is the inner function. Again, I don't know who decided u should be the letter that they use. And then this outer function is what is being done to it. That inner function is being taken to the fourth. When we derive it, we derive the outer function by, in this case, doing a power rule. So power out front, power one less. So that was basically applying your basic power rule. But then the other piece is we had to derive that inner layer. And that inner layer was this u piece. The derivative of that inner layer in this case would be 6x. And so that's what our derivative looked like when we were done with the chain rule. Well, if we're going to integrate something like that, we need to have all the pieces. We need to know what is that inner function, what's happening to it, where is the du, the derivative. We call this the du, the derivative of the inner piece. That's the goal of this last section of the chapter, is how do we work with composite functions, these layered functions, and integrate them. So here's our title of 4.5. It is called Integration by U Substitution. Again, using this letter U to represent an inner function. And we are entirely going to look at composite functions. So working backwards from the chain rule, we know how to derive composite functions with the chain rule. We now need to know how to integrate them by kind of breaking them down. So this chart, I'm just going to kind of talk you through. This is getting you used to how composite functions are built. So in the first column, you see a composite function, some functions having something done to it. We're going to talk about what is that U piece? What is that inner layer? And then what is being done to it, which always sounds funny when you say what is being done to you. Maybe the person who chose the letter U had a sense of humor. And then we also want to talk about what is that derivative of the inner layer, which we're going to call du. So with my first one, x to the fourth plus 2 being squared, the x to the fourth plus 2 is your inner layer, your u. What's being done to it is it's being squared, and the derivative of it is 4x cubed, and the little dx at the end is just reminding you, hey, that's what variable we're working with, because we're kind of going back and forth between this u idea and an x idea. The second one in the chart has a square root of 3x plus 1. The inner layer, the u, is 3x plus 1. What's being done to it is it's being square rooted, or you could say it's being taken to the 1/2 power, which probably makes things a little easier for calculus. And then the derivative of it, the derivative of 3x plus 1 is just a 3. Third one has our inner layer in the bottom. It is a 4x squared plus 2 is your u. Since it's in the bottom and being taken to the fourth, we would say it's being taken to the negative fourth power. And the derivative of it would be 8x. And then my last one, it has kind of some practice with power over root. My inner piece is 2x squared minus 1. It's being taken to the 4/5 power over root, and the derivative of it will be 4x. So we do this to kind of get used to what needs to be present in order to integrate. Derivatives are very flexible. You can derive just about anything with all the different rules. Integrations are not as flexible. Things have to be a certain way in a certain place in order to even make them possible to go through and do. So we're going to start with the absolute easiest version of U substitution for this video, and then we'll get into ones that have some different variations in the future videos. So here's the overall notation. When you are looking at an integral that is made up of a composite function, you're going to have your composite function. So that is that f of u, that inner piece. And then you also need to have the derivative of what's inside. So if that derivative of what's inside isn't there, we have to figure out, can we kind of tweak it to get it there? When we do this, when we integrate, you're truly just integrating by basic power rules. You're going to do a lot of power 1 greater divided by that power. That process doesn't really change. I personally love the FU notation because how many times in my daily life do I get to say FU and actually be talking about math? So another way to write it is you could say you're integrating f of u du. A du, again, is the derivative of the inner function. And when you do that, you end up with this original or general solution, f of u plus c. So here's what we need to look for. We need to figure out what is that composite function, what is the derivative of that composite function, and kind of what are all the pieces and parts. So the absolutely easiest ones that you will see are what I call straight or basic U substitution. And what makes them so nice is they are actually perfect and have everything you need. We say that there's no need to adjust or alter them in any way. So our steps, first step is going to be to write down, well, what is that inner function? And we're going to call that the U piece. So U is x squared plus 1. And then right underneath it, I'm going to write down what is the derivative of that. If you don't write the little dx at the end, it's not a big deal. Then you want to look at the problem and make sure that's what you have. Make sure that you have your U piece having something done to it, in this case being cubed, and then also make sure you have this du piece. We're going to write it now in terms of U. U is kind of like a go-between. We use it as a letter that doesn't get much use any other way to kind of write it as a simpler integral. So what we would say is this is actually U cubed du. That's what's being done to it. It's being cubed. And this du is this derivative, which needs to be there because when you think about how you derive with a chain rule, we need to have that derivative of the inner part. Then we're just going to integrate it. And here's where actually the easiest part is the calculus here. We're just going to do a power rule. Power 1 greater divided by that power. Then we do have to realize we wrote it really simple with U, but we want our answer to be back in terms of x's. So U was kind of, again, just like that go between, that inner step. So my final answer is going to be x squared plus 1 to the 4th over 4 plus c. So we identify our parts, our inner piece and the derivative. We put everything in terms of U. We integrate primarily with power rules. And then we put our x's back in, plug whatever u was back in, so that we get our final answer. So this next one, u is 4x minus 3, because that's the inner piece that's having something done to it. The derivative of that is just 4, which is exactly what you have. You're going to substitute everything back in terms of u's. You'll have your u, you'll have your du. Basically, you transform the original function into u pieces. So it was currently being squared in the bottom, so that's a u to the negative 2. And then the du is going to take the place of everything else that's there, the 4 dx. Power 1 greater divided by that power. You get negative 1 over u, which when you put your x's piece back in for u, you get negative 1 over 4x minus 3 plus c. Now, when you do these, if you want to check your work, we've talked a lot about checking our work this chapter. You just derive what you get at the end. You will have to do a chain rule. Every single one of these will be a chain rule derivative because that's what this process is trying to undo. This one, my u is what's under the radical this time. That's the inner function. The derivative of that inner function is 4x cubed, which you'll notice is exactly what you have. That's what makes this perfect. We're going to look at ones that aren't so perfect and how we deal with them in the next video. So we're going to see what's being done to u. Well, it's currently being square rooted, so we're going to write it as the 1/2 power. And we did confirm that du, that 4x cubed, is there. Power rule, so power 1 greater divided by that power, which we're going to write it as 2/3. Put your x's back in, so sub that u value back in, which was x to the 4th plus 2 plus c. And I've got one more in this video. And again, if you're looking going, okay, these are perfect. What do I do when it's not? I promise that's what's coming. One more perfect one, though, before we start looking at messier ones. So our inner piece this time is x cubed plus 2. The derivative of that inner piece is 3x squared, which is exactly what you have. Sometimes it helps just kind of like, let me show you what I'm replacing here. So this is my du. So what's being done to u? It's currently being taken to the 2/3 power, and you do have the derivative of u as the rest of it. So power 1 greater would be u to the 5/3 over 5/3, which can be rewritten as 3/5. U, I'm going to plug that back in. It's x cubed plus 2 to the 5/3 plus c. And if I want to go in reverse and make sure, did I do this right? If I go through and take the derivative of my final answer with a chain rule, power out front, power 1 last, derivative of what's inside, you would get this original problem. So that is the very basics of how we work with composite functions that are being integrated.